We humans living on a very minor planet and revolving around a very average star are born curious. We began as wanderers and we are still wondering. One question that has troubled mankind since ages is to understand our existence, the existence of this universe as a whole. And to do so, several theories have been put forward time and again to quench the thirst of mankind's curiosity. One such theory proposed in this regime is the string theory. But what it is? Is it the theory of everything? If yes, then why is it so controversial? Well, this is Q&A, and here is the answer to the question, what is string theory? The 20th century was the century of the birth of two of the greatest theories ever. The first one being Albert Einstein's general theory of relativity, a theory that explained the force of gravity and the structure of space-time at macro level, that is, for large objects. And the second one is the theory of quantum mechanics, a theory that gave a completely new and refreshing explanation of the phenomena occurring at micro level. Both these theories work perfectly well in their own domains. By the late 1970s, these two theories had proven to be sufficient to explain most of the observed features of the universe, from elementary particles to atoms to the evolution of stars and the universe as a whole. But when everything seems to have got an answer, nature throws us new problems and questions. And this is exactly what happened with these theories when the problem of quantum gravity knocked at the door of physicists. We know that there are four fundamental forces in nature. They are gravity, that explains the motion of planets around the sun; the electromagnetic force, that explains the motion of charged particles in the electric and magnetic fields; the weak force, that is responsible for radioactive decay of atoms; and the strong force, that binds the protons together inside the nucleus. Einstein's theory of relativity that explains gravity has been formulated within the framework of classical physics, whereas the other fundamental forces are described within the framework of quantum mechanics. So, to describe our universe with a more general theory, to reconcile general relativity with the principles of quantum mechanics, we need a new theory, a theory of quantum gravity. But it's not as simple to formulate as easy it seems to propose. Several difficulties arise when one attempts to apply the laws of quantum theory to the force of gravity, and this is where the string theory comes into the picture. Also known as the so-called the theory of everything candidate, the string theory aims to find out how gravity works for tiny objects like electrons and photons. According to the standard model of particle physics, our current understanding of the universe says that matter is made up of particles called atoms. Atoms are made up of even smaller particles called protons and neutrons with electrons revolving around them. Protons and neutrons are further made up of even smaller particles called quarks, and that's it. But the string theory says that this story doesn't really end like this. Rather, even the smallest fundamental particles are further composed of some one-dimensional objects which we term as strings. So, in other words, the string theory turns the page on the standard description of the universe by replacing all matter and force particles with just one element, the tiny vibrating strings. These magical strings twist and turn in complicated ways. A string of a particular length, striking a particular note, vibrating with a particular energy, gains the properties of a photon, while another string, folded and vibrating with a different frequency, will play the role of a quark, and so on. It's just like guitar strings. As these vibrate, a unique note is created. It is the difference in the vibration of these strings that makes you differ from others. Yes, this is what string theory says. But how does it explain gravity at the quantum level? Well, as we know, each fundamental force has a force carrier associated with it. And in the same manner, a graviton is the hypothetical force carrier associated with the force of gravity. But when physicists try to calculate what happens when two gravitons smash together, they get an infinite amount of energy packed in a very small space, which surely indicates that the math is missing something. This is where string theory comes to the rescue. String theory helps to get rid of the problematic point-like graviton particles and replaces them with strings that can collide and rebound cleanly without implying physically impossible infinites. The pros of the string theory seem to be never-ending. But why is this theory still so controversial? Well, the string math doesn't work in 4 dimensions, which we are familiar with. Rather, it needs 6 additional dimensions visible only to the little strings. Moreover, our technologies have not advanced yet to prove the string theory experimentally. However, despite all these controversies and mathematical complications, string theory is the best contender for a quantum theory of gravitation and remains one of the most active areas of theoretical physics research. And if proved true, it will set up a milestone in itself. Well, that's it for this edition. Make sure you share this video with your friends. See you in the next episode of Q&A.